95 tons. This is the weight of just a single bucket load from some of the massive industrial machines currently operating in quarries around the globe. Why are these mechanical giants built to such a scale that they cannot be transported on standard public highways? It would seem that smaller, more maneuverable equipment could perform the same tasks. But in reality, the sheer volume of material required for global infrastructure makes smaller machines entirely inefficient for moving thousands of tons of rock every single hour. Colossal components arrive at mining sites in dozens of separate shipments, requiring several days of intense labor just to complete the final assembly. One can notice how hydraulic manipulators and heavy-duty cranes lift sections of the chassis that weigh as much as several freight cars. This is just the beginning. The equipment gradually comes to life, and once the massive engines are running, the ground literally shakes under the weight of thousands of tons of steel and counterweights. These machines do not appear in commercials or on dealership floors because their specialized purpose is far removed from the public eye. Everything only gets more complicated as the machines begin their primary task. They operate in remote locations, digging through entire mountains and powering global industries with pure brute force and mechanical precision. It is visible how the massive buckets bite into the earth, removing tons of rock by the minute to reach deep ore deposits. The process is only gaining momentum. One can notice how the dust slowly settles around the tracks of these giants, which remain stationary for months while they reshape the landscape. These units represent the pinnacle of industrial engineering, where every gear and hydraulic line is designed to withstand extreme stresses. But this is not the limit. The largest machine on Earth performs functions that seem impossible for a man-made structure, redefining the very concept of scale in modern manufacturing and extraction. From here, the transition to the next level of mechanical power begins. This concludes the introduction to the world of heavy industrial engineering. 180 metric tons is the total payload capacity of a single heavy-duty machine operating deep within open-pit coal mines. Why is such immense hauling power concentrated in a single vehicle rather than a fleet? At first glance, standard industrial trucks might seem sufficient for transport tasks. But without the specific engineering of the Crest coal hauler, moving the massive volumes of raw fuel required by power plants would necessitate dozens of smaller, less efficient vehicles working simultaneously. One can notice how the machine sits surprisingly low to the ground, despite its immense length of 43 feet, which equals 13 meters. It stands only 16 feet or 5 meters tall, a profile that prioritizes a low center of gravity for stability during heavy loading. This specialized vehicle is a product of the United States-based Crest Corporation. The empty weight of the machine alone reaches 90 metric tons or 200,000 pounds. When the loading shovel fills the hopper to its maximum limit, the total weight surges as it takes on over 400,000 pounds of coal. The process is only gaining momentum. 1,200 horsepower is generated by the massive Caterpillar 16-cylinder engine positioned at the heart of the chassis. With a displacement of approximately 1,650 cubic inches or 27 liters, this power plant provides the necessary torque to move the loaded hauler. It is visible how the vehicle climbs steep, dusty inclines within the mine as the heavy-duty automatic transmission shifts to manage the strain. The rear-wheel drive system pushes the weight forward, while the reinforced hydraulic suspension absorbs the shocks of the uneven, unpaved terrain. Everything only gets more complicated when navigating the tight turns of an extraction site. 10-foot tires, measuring 3 meters in height, rotate slowly under the pressure of the payload, resembling components from a giant tractor. One can notice the unique geometry of the dump bed, which features a curved design specifically engineered to maximize the volume of coal carried in every trip. The operator sits in a side-mounted cab that extends outward to provide a clear line of sight over the massive mechanical frame. These haulers move material continuously from the deep extraction points to the primary crushers and processing zones. But this is just the beginning. Efficiency is the primary reason mining companies integrate these giants into their daily operations. A single Crest unit effectively replaces an entire fleet of conventional trucks, reducing traffic congestion on the narrow haul roads of the open-pit mine. It only looks obvious to treat these machines as mere tools, but in reality, many mining crews develop a personal connection to the equipment. Some units are decorated with custom paint jobs or assigned specific names. serving as mechanical mascots for the laborers working the coal seams. The vehicle completes its cycle by depositing the coal at the processing station. A machine built to push the massive loads the crest carries is already positioned for the next phase of the operation. 152 metric tons is the weight of the massive steel structure that makes up the Komatsu D575A3SD Super Dozer. Why is such an immense volume of metal concentrated into a single crawler machine? It would seem that multiple smaller units could cover more ground simultaneously. But without this concentrated mass and power, the toughest mining and earth-moving tasks on the planet would remain unfinished, as smaller equipment lacks the raw physical force required to move tens of cubic meters of dense material in one motion. Japan serves as the manufacturing origin for this specialized crawler dozer, which is engineered specifically for the most demanding environments. It measures 11.7 meters in length and stands 4.9 meters tall. The machine carries a blade that spans 7 meters in width, creating what functions as a moving wall of steel. At first glance, the dozer appears to be a static monument, but in reality, it is a highly mobile piece of industrial equipment. The power source for this machine is a Komatsu SA12V170E V12 engine. This unit has a displacement of 46 liters, or 2,800 cubic inches, and it generates 1,150 horsepower. One can notice how the low rumbling of the engine signals the release of immense energy as the machine begins its work. Everything only gets more complicated as the load increases. Pushing up to 69 cubic meters of material in a single pass is the primary function of this super dozer. This volume represents more dirt and rock than would fit inside an entire residential room. The automatic transmission is equipped with long gear ratios, which are designed to provide sustained torque during heavy-duty operations. It does not end at this stage. Stability is maintained through a rigid suspension system paired with crawler tracks that grip the rough terrain. The massive blade requires the constant guidance of a ground crew when the operator performs tight maneuvers in restricted spaces. It is visible how the equipment gradually shifts thousands of tons of coal or earth with unstoppable momentum. The process is only gaining momentum. Large-scale coal mining operations in the United States and Japan are the typical environments where these machines are deployed. Often, a single D575A-3SD replaces a fleet of smaller dozers, performing their combined work with higher efficiency. Remote areas also utilize this machine to level vast plots of land in a short time frame. Transition to the next level. Transportation of such a giant presents significant logistical challenges. For instance, when one unit was transported to a trade expo in Texas, the unloading process alone required 2 full days of continuous labor. Boulders and earth split with a crack when the machine engages the ground. Yet this is just the beginning of industrial scale. The next machine in the sequence is capable of carrying this entire dozer on its back, while maintaining extra capacity. The D575A-3SD concludes its work by leaving a perfectly leveled path in its wake. This stage of the earth-moving process is now complete, allowing the material to move to the next phase of the mining operation. 4,000 horsepower is the output generated by the massive engine housed within the Caterpillar 797F. Why is such an immense amount of power required for a single vehicle? It would seem that a standard industrial engine could move a large frame, but the sheer physics of hauling 400 tons of rock uphill across rugged terrain requires a displacement of 106 liters. This mechanical titan is engineered specifically for operations in the most expansive iron, copper, and coal mining sites on the planet. 49 feet or 15 meters is the total length of this machine, which stands 23 feet tall. One can notice how the operator must climb what essentially constitutes a 2-story staircase just to reach the control cab. With the side mirrors fully extended, the width of the vehicle reaches nearly 33 feet or 10 meters. At first glance, the proportions seem impossible for a mobile unit, but in reality, every inch is calculated for maximum stability. The process is only gaining momentum as one considers the weight of the structure. The equipment gradually tips the scales at over 1,500,000 pounds when fully loaded, which equals 687 metric tons. Even without a single boulder in the dump bed, the empty chassis weighs over 575,000 pounds, or 260 metric tons. Power flows through a Caterpillar C175 20V20 engine with 6,488 cubic inches of displacement. It gets more complex further on. A 7-speed automatic transmission is fine-tuned to manage this energy, delivering force primarily through a rear-wheel drive configuration. Heavy-duty suspension systems work in tandem with electronically managed braking to ensure safe descents down steep mine ramps. It is visible how the 4 main tires, each standing nearly 13 feet tall or 4 meters, support the entire frame. Each individual tire represents an investment equivalent to the cost of a small automobile. Everything only gets more complicated when analyzing the payload capacity. The dump bed is designed to transport up to 400 tons of material in a single operation. To match the volume of just one load from this truck, a fleet of approximately 40 standard dump trucks would be required. One can notice the efficiency this brings to the extraction cycle in massive quarries. But this is just the beginning. The camera glides along the massive steel bed, which has become a staple in documentaries and mining simulators due to its iconic status. In the large mines of Canada, operators describe the experience as commanding a vessel rather than simply driving a vehicle. The scale of the 797F is so significant that it has been featured in international exhibits as a feat of American engineering. This machine concludes the current phase of heavy hauling, while even larger designs continue to push the boundaries of mechanical size. 800 tons. Such is the total moving mass of the Belaz 75,710 when its bed is filled to capacity. Why was such an extreme engineering scale necessary for a single vehicle? It would seem that a fleet of standard trucks could manage the same volume of rock. But in reality, this Belarusian colossus replaces entire columns of smaller machinery, drastically reducing operational costs and the time required for logistics in massive open-pit mines. The machine measures 67.5 feet in length, or 20 6/10 meters, while the width reaches 32 feet, which equals 9 7/10 meters. One can notice how the operator cabin, mounted to the far side, appears microscopically small compared to the steel expanse of the main chassis. This structure rises 26.5 feet into the air, or 8 1/10 meters from the ground to the upper rim. Everything only gets more complicated when considering the sheer weight of the components. The empty frame alone weighs 793,000 pounds, or 360 metric tons. Once the massive hydraulic shovels finish loading, the truck carries an additional 992,000 pounds, equivalent to 450 metric tons of material. It is visible how the tires, standing nearly 13 feet tall, support this pressure. But this is just the beginning of its technical complexity. 2 MTU diesel engines, each a 20-cylinder V configuration, generate 2,300 horsepower apiece. Combined, they produce a total of 4,600 horsepower. This energy does not travel directly to the wheels through a traditional mechanical link. Instead, the diesel units feed a sophisticated diesel-electric drivetrain, where 4 independent electric wheel motors provide the actual propulsion. The process is only gaining momentum as the electronic transmission coordinates the output. 8x8 all-wheel drive allows the Colossus to maintain traction on the uneven terrain of deep quarries. The equipment gradually compensates for the immense weight through a hydropneumatic independent suspension system. This ensures that the vehicle handles extreme loads with a level of stability that contradicts its massive dimensions. The camera glides along the side of the chassis to reveal a fuel tank designed for long-duration shifts, holding more than 1,300 gallons or 5,000 liters of diesel. Ascending to the control center requires climbing a staircase that reaches the height of a 3-story building. From this vantage point, the truck operates within the vast open-pit mines of Kazakhstan and Russia, moving mountains of earth in a single pass. In 2014, these capabilities earned the machine a Guinness World Record as the highest capacity haul truck on the planet. And this is not the limit of heavy engineering, as that record remains unchallenged to this day. The focus now shifts from the transport of materials to the machines designed for total structural demolition. This next specialized apparatus does not merely move soil or rock. It possesses the mechanical force to swallow entire buildings whole. 811 metric tons is the total operating weight of the Hitachi EX8000-6, a machine that redefines the limits of hydraulic excavation. Engineered in Japan by Hitachi Construction Machinery, This apparatus is specifically designed for the world's most intensive mining environments where standard equipment would fail. The physical dimensions are staggering, as the structure stretches to a length of 15 meters and reaches a height of 10 meters when the boom is fully extended. Why is such immense scale necessary for modern mining operations? It might seem that smaller, more mobile units could perform the same task with less fuel. But in reality, the economic viability of a massive copper or coal mine depends entirely on the volume of material moved per hour, and a smaller fleet simply cannot match the throughput of a single giant. Two Cummins QS-K60 engines provide the mechanical heart of the excavator, consisting of two V16 power plants that generate a combined output of 3,880 horsepower. This energy is channeled through a hydrostatic transmission system featuring independent hydraulic circuits. One can notice how the arm movements remain smooth and consistent even when the bucket is under a maximum load. But this is just the beginning. The hydraulic arm is capable of lifting 45 cubic meters of rock and earth in a single pass, which translates to approximately 75 tons of material. To put this into perspective, the bucket is wide enough to hold two full-size cars side by side. It is visible how the wide crawler tracks and the reinforced chassis suspension absorb the violent impacts of non-stop operation in harsh terrain. It only looks obvious that such power would be difficult to manage, but in reality, the operator sits in a climate-controlled, sound-insulated cabin equipped with bulletproof glass and advanced digital interfaces. The equipment gradually fills a 300-ton haul truck in only 4 to 5 passes. This efficiency turns what would normally be hours of loading time into a matter of minutes. The process is only gaining momentum. Specialized adaptations have expanded the utility of this model even further, such as a unit modified for a lithium mine with corrosion-resistant hydraulics. This specific engineering solution now serves as a technical case study for the entire mining industry. These machines are currently active in the massive gold and coal deposits of Australia, Canada, and Chile. The mission of the machine remains the movement of the maximum possible volume of material in the fewest cycles necessary. From the reinforced boom to the heavy-duty tracks, every component is synchronized to maintain this output. The excavator completes its cycle and rotates back toward the rock face to begin the next pass. Thus, the massive machine continues its work, maintaining the flow of raw materials required for global production. 1,270,000 kilograms is the total mass of the Bucyrus 495 HR, a machine that defines the sheer scale of modern surface mining. Why is such immense weight necessary for a single piece of equipment? While a smaller excavator might struggle against the resistance of the earth, this mammoth electric rope shovel utilizes its 2,800,000 pounds of structural bulk to remain anchored while tearing through the landscape. The machine stands approximately 50 feet tall at the peak of its boom, which is roughly 15 meters, and stretches nearly 100 feet in length from the rear of the housing to the tip of the bucket. But this is just the beginning. The equipment gradually moves not by the combustion of diesel, but through high-voltage electric cables that snake across the quarry floor to provide constant energy. Massive electric motors drive the internal systems responsible for hoisting, swinging, and digging, with each mechanical sequence timed to a level of industrial precision that eliminates wasted motion. One can notice how the hydraulic systems constantly adjust to balance the towering structure as the shovel engages with the rock face. The bucket can lift over 120 short tons, or 90 metric tons, in a single scoop. It seems simple to move such a volume, but in reality, the mechanical electric drivetrain must translate thousands of kilowatts of power into a smooth, steady pull. The shovel travels on gigantic crawler tracks, with each individual track being wide enough to support the weight of a full-sized freight locomotive. Everything only gets more complicated when considering the sheer volume of the front bucket, which holds up to 157 cubic yards or 120 cubic meters of material. The boom extends over 100 feet or 30 meters, appearing like a mobile steel tower that methodically excavates the earth. At first glance, the operation of such a giant might seem clumsy, but the high-mounted cab provides the operator with full visibility and access to specialized precision controls. These machines are utilized in coal and iron mines across the United States, Canada, and South Africa to prepare sites for deeper extraction by clearing top layers of soil and rock with relentless efficiency. The process is only gaining momentum as these shovels continue to function decades after their initial deployment. Even after Caterpillar acquired Bucyrus in 2011, many operators still refer to the equipment by its original name as a mark of industrial respect. One specific unit in Wyoming has been operating for over 20 years, requiring only minimal updates to its core systems during that time. This shovel successfully clears the path for the next phase of the mining cycle, where heavy lifting moves to an even more intensive level of performance. 3 million pounds is the staggering weight of the Komatsu P and H4800XPC, an industrial giant engineered specifically for the most punishing mining environments on the globe. Why is such immense scale necessary for a single piece of equipment? While a standard excavator might struggle with the sheer volume of rock in a massive quarry, this machine functions as a mobile epicenter of production, designed and assembled within the United States to dominate the landscape of the largest mines on the planet. The machine is so vast that from a distance, its silhouette is easily mistaken for a stationary factory rather than a mobile vehicle. One can notice how the boom reaches upward to a height of over 100 feet, which is more than 30 meters into the air. The shovel operates with nearly 10,000 horsepower, drawing its immense energy directly from high-voltage grid-connected cables that feed its massive electric motors. It seems simple to move such a weight, but in reality, the shovel's lifting, crowding, and swinging mechanisms must perform with surgical accuracy to avoid structural failure. The chassis spans nearly 65 feet in width, or 20 meters, providing a stable foundation for the mechanical forces at play. Transition to the next level. The bucket serves as the primary tool of extraction, possessing the capacity to lift up to 135 short tons, which equals 122 metric tons of material in a single motion. It is visible how the steel teeth bite into the earth, moving enough rock and dirt to fill an entire 6-story building in mere seconds. This component is the centerpiece of the machine's efficiency, allowing it to clear massive sections of a mine face with minimal passes. Everything only gets more complicated when considering the physics of the movement. Industrial-scale crawler tracks support the 1,400 metric tons of steel, moving the unit across the uneven floor of the mine. Advanced shock-absorbing systems are integrated into the frame to mitigate the relentless structural stress generated during repetitive digging cycles. At first glance, the motion looks rigid, but the integrated suspension and a rotating base allow the shovel to maintain full balance at all times, even when the bucket is at its maximum extension. The design resembles a hybrid between a high-capacity crane and a mobile refinery, reflecting its complex internal systems. The process is only gaining momentum. The operator cabin is mounted high above the ground to provide a clear vantage point over the massive work area. It includes automated controls and redundant safety systems, alongside a 360-degree monitoring setup that ensures the surrounding environment remains clear of obstacles. These electronic eyes allow for continuous operation in coal and copper mines across the United States and Canada, where the machine runs for up to 22 hours every day. Only brief windows of downtime are permitted for essential maintenance. One can notice a specific unit painted in red, white, and blue, bearing the nickname Liberty as a tribute to the industrial strength of the nation. This machine represents the peak of electric rope shovel technology, where every gear and cable is optimized for maximum throughput. It does not end at this stage, as the engineering required to move such mass must also account for the longevity of the metal under constant friction. The 4800XPC concludes its shift by clearing the path for transport trucks, ready to repeat the cycle. The material is moved to the next processing phase without haste. 57.5 feet is the massive diameter of the cutting face that defines the scale of this engineering feat. Why did the Washington State Department of Transportation commission a machine of such unprecedented proportions? At first glance, boring through a dense urban center seems impossible, but this specific technical solution was required to construct the State Route 99 tunnel beneath the heart of Seattle. The machine, christened Bertha, was engineered by Hitachi Zosen in Japan to navigate approximately 2 miles of diverse geological strata. This distance, spanning 3 kilometers, represents one of the most difficult subterranean environments in North America. For a significant period, the unit maintained the global record for the largest tunnel boring machine by diameter. It measures 330 feet in length, which is equivalent to 100 meters, and possesses a total mass exceeding 7,000 tons. 25 independent electric motors generate the immense power required to drive the operation. This system produces more than 8,000 horsepower, allowing a massive cutter head to rotate with enough force to penetrate obstacles. It is visible how the rotating face, equipped with specialized steel discs and hardened blades, grinds through a varying mixture of solid rock, loose soil, sticky clay, and reinforced concrete. But this is just the beginning of the internal complexity. The drive system integrates these electric motors with a secondary hydraulic assist to manage the resistance of the earth. The machine advances through the ground inch by inch, propelled by a sophisticated network of hydraulic thrust cylinders that push against the newly installed tunnel walls. One can notice the slow, deliberate movement of the shield as it slides along integrated guide rails. Inside the outer steel shell, the structure functions as a self-contained underground factory. It houses dedicated control rooms, complex electrical and mechanical arrays, and specialized ventilation systems to maintain air quality for the personnel. Everything only gets more complicated when considering the logistical flow of materials. Conveyor systems run ceaselessly to transport excavated debris from the front of the machine to the surface. It seems simple to just dig a hole, but in reality, the machine must simultaneously excavate and install the structural lining. As the cutter head advances, mechanical arms place precast reinforced concrete segments into a perfect circle. This process creates the permanent roadway structure in the machine's wake while maintaining the integrity of the earth above. Precision is absolutely critical because the path of the tunnel runs directly underneath skyscrapers, active highways, and pressurized water mains. The camera glides along the massive internal workspaces where the rotating crew manages the delicate balance of pressure and alignment. The project faced significant technical challenges, including a major mechanical breakdown that required a prolonged period of complex repairs. Despite these setbacks, the machine successfully reached its destination and completed the bore in the year 2017. Following the breakthrough, the massive structure was decommissioned and carefully dismantled into manageable sections. 7,000 tons of machinery did not simply disappear after the project concluded. It is visible how specific components of the machine were repurposed into public art installations. These remnants are now situated in the parks of Seattle, serving as a technical tribute to the most ambitious infrastructure project in the history of the city. The process concludes this phase, opening the road to even larger industrial giants. 500 feet is the approximate length of the legendary machine known as Big Muskie, a record-breaking piece of engineering that defined the concept of scale in the 20th century. Why did such a massive construction become necessary for industrial operations? Surface mining in the United States required the removal of immense layers of earth to reach coal deposits, and standard equipment simply could not keep pace with the demand for efficiency. Manufactured in 1969 by the Bucyrus Erie Company, this electric dragline excavator occupied the position of the largest earth-moving machine on the planet for several decades. It stands 70 feet tall at the level of the operator cab, while the massive boom extends 310 feet into the sky. One can notice how the structure resembles a stationary industrial complex rather than a mobile vehicle. The total operating weight of this giant exceeds 13,000 tons, a mass roughly equivalent to 2 small aircraft carriers combined. But this is just the beginning. The equipment draws its power from high-voltage electric lines that snake across the terrain of the mine. These cables feed a network of internal motors that generate more than 18,000 horsepower to drive the mechanical systems. The camera glides along the heavy steel cables that control the hoisting and swinging mechanisms used to manipulate the primary tool of the machine. That bucket is capable of holding nearly 222 cubic yards of earth in a single scoop. This volume translates to approximately 295 tons of rock and soil lifted in one clean motion. At first glance, the process of removing overburden seems like a slow labor, but in reality, the sheer scale of the bucket allows for the clearance of entire sections of the landscape in minutes. The process is only gaining momentum. Mobility for a machine of 13,000 tons presents a unique mechanical challenge. Big Muskie does not use traditional wheels or continuous tracks, but instead relies on giant walking pads that function like enormous mechanical feet. The machine slowly repositions itself by lifting its entire frame and shifting its weight forward in measured increments. It is visible how the metal feet press into the soil, and some repositioning maneuvers are so complex that they take several days to complete. Operators reach the elevated control cabin by navigating a series of internal staircases and metal walkways built directly into the skeleton of the excavator. For years, this machine worked the strip mines of Ohio, stripping away the thick layers of soil and rock to expose the coal buried deep beneath the surface. Everything only gets more complicated when considering the total volume of material moved over its lifespan. Estimates suggest that Big Muskie relocated over 600 million tons of earth during its decades of active service. After being decommissioned in the 1990s, the vast majority of the steel structure was dismantled for scrap. However, the legacy of the project was not entirely lost to history. The massive bucket was preserved in its entirety and now sits on public display as a monument to American industrial engineering. It only looks obvious that such a machine would represent the peak of mechanical size, but in reality, the limit of human engineering extends even further. The final machine on this list is not merely large, but stands as the single largest mobile machine ever constructed in human history. 14,200 metric tons is the total mass concentrated within the frame of the Bagger 293, the largest terrestrial mobile vehicle in existence. Why was such a colossal structure conceived for the open pit mines of Europe? It would seem that smaller, more agile excavators could manage the extraction of lignite, but in reality, the sheer volume of brown coal required by modern power plants demands a scale of movement that only a machine of these proportions can provide. One can notice how its steel lattice stretches across the horizon, reaching a total length of 738 feet, or 225 meters. Germany served as the birthplace of this engineering achievement in 1995. The industrial firms Takraf and Siemens collaborated to design and manufacture the giant specifically for the extraction of lignite in high-capacity mining environments. At first glance, its height of 315 feet or 96 meters makes it appear stationary. But this is just the beginning. The machine is capable of autonomous movement, although repositioning its 31 million pounds of weight within the confines of a mine is a process that can occupy several full days of precision maneuvering. The heart of the excavation process is a massive rotating bucket wheel situated at the end of the primary boom. 18 individual buckets are mounted around its circumference, each designed to scoop 8.6 cubic yards or 6.6 cubic meters of earth in a single rotation. It is visible how the wheel bites into the layers of the earth, extracting up to 8.5 million cubic feet of material in a single 24-hour cycle. The process is only gaining momentum as the excavated soil is transferred immediately onto internal conveyor systems. One can notice that the propulsion of this entire complex is strictly electric. High-voltage cables connected to the local power grid supply 16,500 horsepower across a network of specialized motors. This energy is distributed to the tracked undercarriages and steering mechanisms that allow the structure to glide across the uneven floor of the open pit. Inside the main frame, the equipment gradually reveals its complexity, containing technical rooms, maintenance corridors, and localized equipment stations. Everything only gets more complicated as the machine transitions from a simple tool into a self-contained industrial facility. Operators manage these vast systems from an elevated cockpit that provides panoramic views of the entire excavation face. Digital command systems allow for the simultaneous coordination of the bucket wheel rotation and the downstream conveyor belts. Currently, the Bagger 293 remains operational in the Hambach open pit mine in Germany. The lignite it extracts serves as a primary fuel source for nearby power plants, directly influencing the energy stability of entire regions. Beyond its technical function, the machine has established itself as a cultural icon within the industrial world. It has been documented in various technical exhibitions and even served as the focal point for nighttime art performances involving synchronized light shows and music. Transition to the next level. Despite these artistic uses, its primary purpose remains the relocation of Earth on a scale that no other land-based machine can match. The Bagger 293 represents the absolute limit of terrestrial industrial size. moving more material than any other vehicle ever constructed. The machine continues its ceaseless rotation, maintaining the flow of resources to the processing facilities. Thus ends the overview of the most massive mobile machine in the history of mining engineering. 100% of the heavy machinery described represents a redefinition of industrial limits rather than a simple extension of existing capabilities. Why do these massive structures exist in such isolation? It seems simple to assume they are merely larger versions of standard equipment. But in reality, their engineering is a monument to overcoming physical impossibilities through calculated design. These high-powered haulers and monster excavators do not operate within urban environments, instead performing their functions in the deep shadows of remote mines or far beneath the Earth's surface in locations isolated from civilization. One can notice how the impact of these steel giants resonates far beyond their remote workstations. The process is only gaining momentum as these machines power entire nations and provide the essential fuel for global industries. It is visible how the Earth itself is reshaped by the constant movement of these moving cities of steel. Everything only gets more complicated when considering the scale of the logistics required to maintain such equipment in the world's most extreme environments. Technical mastery is required to manage machines that conquer the most hostile conditions on the planet. The transition to the next level of industrial understanding happens when one realizes these giants are the silent foundation of modern infrastructure. The movement of these mechanical systems concludes this phase of the technical overview. Thus, the exploration of heavy industrial equipment reaches a point of completion for this specific segment of the production cycle.